Hello everyone, my name is Karan and today I'm going to talk about our work on understanding task transfer in vision language models. VLMs have achieved good performance on a variety of tasks. However, they still fall short of human performance on perception tasks like counting, spatial reasoning, and relative depth. In the current paradigm, they're often fine-tuned on one of these tasks, let's say counting, and they get good results on it. But if you fine-tune on counting, what happens to spatial reasoning? What happens to relative depth? There are many unknown interferences on other tasks, and we have no understanding of how these tasks interact with each other. The first paper to study these task relations was back in 2018 in the era of CNNs, called Taskonomy. Since then, there has been works focusing on pre-training focused transfer studies, analysis of latent factors, and the effect of SFT and RL. However, our position is a bit different. We aim to study zero-shot task transfer through fine-tuning. More precisely, we ask the question, how does fine-tuning on one perception task affect zero-shot performance on other perception tasks? Essentially, if you fine-tune on a single task, what is its effect on a bunch of other tasks that you have? So we start by describing our setup. We take a pre-trained VLM and perform LoRa fine-tuning on it for a single task. This fine-tuned model is then evaluated on all the tasks that we have. This is repeated for the whole task suite. For that purpose, we utilize the Blink benchmark that offers a variety of perception tasks, like reasoning, correspondence, depth, and so on. For all of these tasks, we build fine-tuning datasets, and all fine-tuned models are evaluated on the whole benchmark. For the pre-trained VLM, we utilize Qwen 2.5 VL across different model scales, and all the fine-tuning is performed across random seeds to rule out any spurious noise that may occur. So with this setup, we aim to obtain a task transfer matrix. A task transfer matrix essentially has all the rows as source tasks on which we perform fine-tuning, and all the columns as target tasks on which we evaluate the fine-tuned model. Each cell represents the transfer from the source task to the corresponding target task, which is quantified by the transferability score. So a positive score means positive transfer, and a negative score means negative transfer. So using this transferability score, we can also define task transferability. So the aggregation of positive transferability scores in a row is termed as the positive task transferability. And similarly, we can define negative task transferability. These give a general sense of how the source task functions in the transfer ecosystem. We also introduce another term called malleability. So the aggregation of transferability scores in a column is termed as that task's malleability. It helps measure how sensitive a target task is to fine-tuning on other tasks. So if a task has high positive malleability, it can get easily improved by other tasks. It has high negative malleability, then it can get easily deteriorated by other tasks. So now we've defined the task transfer matrix, transferability, as well as malleability. However, all these three things are contingent on the transferability score. What metric should be used for quantifying this transferability score? A naive way to go about this would be to just use raw accuracy gain, but that quickly falls apart. Consider this toy example where task A and task B lead to a raw accuracy gain of 3 and 5 points. Since 5 points is greater than 3, it would exhibit a greater transfer, but that is quite misleading. One can argue it is much harder to go from 90 to 93% than it is to go from 40 to 45%. Hence, we need some normalization term here to account for the task difficulty. For that purpose, we introduce a new metric called perfection gap factor, or PGF. It can be interpreted as the change in accuracy after fine-tuning, divided by the remaining headroom to upper bound accuracy. So this could be 100 minus the current accuracy, or human performance minus the current accuracy. And a positive PGF means positive transfer, and a negative PGF means negative transfer. So now, using this defined setup and metrics, we obtain the task transfer matrix, and we use that to create a task graph. A task graph essentially has each node as a task, and the edges signify the relationship between the tasks. These structures help us to gain several inferences, which I will now talk about. So for our first key takeaway, we find that the magnitude of positive transferability and positive malleability increases with model size. So as we go from a 3 billion model up to a 32 billion model, all the positive trends and relations that we see strengthen and increase with the model size. And surprisingly, we find no such trend for negative transfer. It is only the positive transfer that increases with model size. Next, we look into trends based on task categorization. So the benchmark itself provides a task categorization into low, mid, and high-level tasks. We find that low-level tasks are highly positively transferable and highly positively malleable. What does this mean? It means that if you were to fine-tune on low-level tasks, most tasks would get improved. And the reverse is also true. If you were to fine-tune on most tasks, low-level tasks would get the most benefit. So low-level tasks are the ones that impart the most benefit and also gain the most benefit. Next, we also find these interesting structures within our task graph, which we call as cliques. So these are mutually beneficial and mutually deteriorative clusters of tasks. Here's an example of a positive and negative clique that we observe. Moreover, we also define some task characteristics, or as we like to call them, task personas. So donor tasks, as the name suggests, helps many other tasks and have high positive transferability. Its counterpart are pirate tasks, which hurts many other tasks and have high negative transferability. In our case, we found functional correspondence to be a pirate task, which might be related to its task complexity. Next, we define sponge tasks, which can get easily improved by other tasks and have high positive malleability. These also share an intersection with the low-level tasks that we discussed earlier. Lastly, we have sieve tasks that can get easily deteriorated by other tasks and have high negative malleability. Lastly, we also study some transfer to video tasks. Essentially, we take the fine-tuned models on the image tasks in the Blink benchmark and then evaluate them on video tasks on VSI bench. And surprisingly, we find the same task persona trends appearing in the video domain as well. For example, depth appears as a sponge task in both image as well as video tasks. So all this analysis is quite interesting, but what are the practical applications for this? We believe this has practical implications from dataset curation, better learning paradigms, as well as benchmark design. We aim to illustrate an example for that for better dataset selection. So consider a scenario where we have a pre-trained VLM, and we want to optimize its performance on a task, let's say counting, but we have no data for counting. Instead, we have access to related tasks like relative depth, correspondence, similarity, and so on. So how would we achieve good performance on counting? We can take the previous analysis and find which tasks transfer the most to counting and create an informed data mixture from the other tasks. And we find that this informed data mixture can actually match and even exceed performance of directly fine-tuning on counting. And this has several implications in creating efficient data mixtures. So to conclude, we present a systematic study on a broad suite of perception tasks. We introduce a new metric called PGF to enable this analysis, as well as present a downstream application in the form of better dataset selection for fine-tuning. We hope this would be useful for future practitioners. Thank you. Please feel free to ask questions.